Hello again, my dear students, and welcome to the second part with our optical laser course or optical systems course in the laser amplification and oscillation lecture. If you remember, my dear students, we have terminated part number one with this three-level gas laser model, where we have demonstrated together how we can write the rate equation for level number one and level number two. So for level number two, we said that the rate of a change of the popularity, which is N2 for the level energy E2, with respect to time, dN2 by dt is equals to R2 of t, which represents the injection of electrons from the ground state to the energy level E2. Of course, this add to the popularity, that's why it's a positive sign. Then we have two types of spontaneous emission. We have a spontaneous emission from N2 to E1 and from E2 to E0. These both, those both spontaneous emissions are concluded in this term N2 over tau 2. Then we have stimulated emission and absorption occurs between the energy level E2 and E1, which is summarized by the term sigma I over h mu N2 minus N1. Of course, spontaneous emission acts toward decreasing the popularity. That's why it's negative. Same like for the stimulated emission, while absorption acts to increase the popularity. That's why it's been positive. Similarly, for the layer number one, or the energy level number one, we say that dN1 by dt is equals to R1 of t, which is the injection rate from the ground state to an E1 state. Again, it's a positive sign because it's add positively. Then we have the spontaneous emission dropping from E2 to E1, which of course will add the popularity of E1, so it's plus N2 tau 2 1. And then we have the stimulated emission in positive, because now the stimulated emission from E2 to E1 will add positively to E1, while the absorption from E1 to E2 will add negatively to E1. And finally, we have the spontaneous emission from E1 to E0, which is N1 tau 1. So these two equations are considering the main two rate equations for the three-level laser. Okay, what we are going to do now, my dear students, is that we are going to try to solve these two differential equations. But again, please don't forget why we are doing these tasks. We are doing these tasks to show the continuity in the gain inside an optical cavity. What I mean, based on what we studied regarding the selectivity of a resonant frequency to be amplified based on this gain condition, we have found that this process is a continuous process. I mean, per each round trip, the resonant frequency centered with respect to the gain coefficient will be amplified. And this amplification process will tend to infinity, which is something unrealistic. So what we are going to do now is that we are going to solve these two equations together to show, is this realistically an infinite gain or not? So in order to make this equation a bit simple, in the first assumption or in the first attempt, because we are going to solve these equations 3 times with 3 different assumptions. But let's start with the most simple assumption. Herein, in the most simple assumption, we will assume that N2 is much greater than N1, which is actually a very logic assumption, because this agrees with the gain condition we have demonstrated in the beginning of the lecture, and we already have demonstrated in chapter 3 in the atomic radiation lecture. When we say that one of the condition for gain, or the condition to have a gamma positive, we should have N2 much greater than N1 or greater than N1. So herein, it makes sense to say that N2 is much greater than N1. This is the first assumption. The second assumption is to say that tau 2 is greater than tau 1. What is tau 2 and what is tau 1? Tau 2 represents the lifetime of the particle or of the electron in the energy level E2. And tau 1 represents the lifetime of the electron in the energy level 1. As you know, the rate is 1 over tau 2. So when tau 2 is much greater than tau 1, that means that the lifetime of the photon, of the electron in tau 2 is greater, which means that the rate for the spontaneous emission is smaller in case of in case of level 2 with respect to level 1. Okay. So let me now open my camera and start doing this solution. Okay, perfect. Let's start with the equation for the energy level E2, which is saying that dN2 by dt equals to, first we have R2, then we have minus N2 over tau 2, then we have minus again sigma I over h mu N2 minus N. This is the rate equation for the energy level. Now, what you say that our assumption is N2 is much greater than N1. Accordingly, using this assumption, you can easily say that this term, which is N2 minus N1, will tend to N2, and you can ignore N1. So we can rewrite this equation saying that dN2 by dt equals to R2 minus N2 over tau 2 minus sigma I over h mu N2. Perfectly. Then, in order to make the solution more and more easy, let's assume thermodynamic equilibrium condition, steady state condition. I mean, let's assume dN2 by dt will be equal to 0. If you remember, we do the same approach while we are dealing with the atomic, with Einstein approaches, Einstein coefficients in the atomic radiation lecture. So now I will assume a steady state condition. So your equation will be rewritten in the form 0 equal R2 minus N2 over tau 2 minus sigma I over h mu N2. Now you can transfer this to the other side with a positive sign, and we have an n common factor, N2. So N2 equal N2 times 1 over tau 2 plus sigma I over h mu. This is equals to R2. Accordingly, you can say that N2 equals R2 over 1 over tau 2 plus sigma I over h mu. Or you can write it in a more decorative manner by multiplying by tau 2 in both numerator and denominator, and get R2 tau 2 equals 1 plus sigma I tau 2 over h mu. So this is an equation for n. Okay, so you can ask me now, what is the benefit of having this equation? This is just an equation that represents the popularity in the level N2, assuming a steady state condition, and assuming that N2 is much greater than N1, of course. And it's just a closed form for N2. That's all. But how we can make use of this equation? Let's see. Okay, let's return back to one of the important equations we have studied together. which is di by dz equals gamma times r. If you remember, this is the gain equation. If you remember, my dear student, gamma is equals to sigma times gamma equals to sigma times n2 minus n. You can return back to the equations in the first lecture, in the first slide of this lecture, or in the equation for the atomic radiation lecture, the last slide. Of course, there is always G2 over G1, while we are assuming now in G2 over G1 is equals to 1. That's why we have it like that. Accordingly, and based on our principal assumption that N2 is much greater than N1, so you can say that gamma is equals to sigma times N2. Okay, what is gamma? Gamma is the gain coefficient. What is N2? 1, 2 is the population in the energy level number 2. What is sigma? Sigma is the stimulated emission cross section. We already have an expression for N2. This expression. Okay, that's perfect. So we can multiply this expression by sigma. So gamma equals sigma R2 tau 2 over 1 plus sigma I tau 2 over h. This is an expression for gamma. Okay, where is the issue? Let's call this term gamma node. And let's call the term h mu over sigma tau 2 is, or any constant, just to make the equation more easy. Then you can rewrite the equation, this equation, in this form. Gamma equals gamma node, which is this term, 1 plus I over is. I just pick up this term and call it is. So it's now I over is. Okay, again, okay. So after solving these two differential equations, we have concluded this equation for the gain of. So let me rewrite this equation again, because this equation is very important. So gamma equals to gamma node over 1 plus I over is. Gamma node and is are constants. So it's a relation between gamma and the I, where I is the intensity. So let's start to think about this equation. Assume now that you have your cavity. Okay, so this man is out of service. Yeah. Assume that you have now your cavity. If you remember, we say that this cavity will be initiated or seeded by a very, very, very small intensity in the beginning of the cycle. So let's assume that in the beginning, I is equal to 0. Okay, perfect. So intensity is equal to 0 in the beginning. What about the gamma? Gamma will be equals to gamma naught. Okay, then the intensity will start to propagate inside the optical cavity. And as far as you have a gaining medium inside, this intensity will going to be enlarged. It will going to be amplified. So let's say that the intensity will start to be is. Any value. If the intensity tends to be is, then this is is over is, which is 1, 1 plus 1 is equal to 2. So gamma will be equals to gamma node over 2. Then the intensity will be 2is, for example. Then you have here 2 plus 1, 3, then gamma will be equal gamma node over 3, and so on. So as far as the intensity amplified inside the optical cavity, the gain coefficient associated with the intensity is decaying. When the intensity reaches the maximum, which is ideally infinity, the gain will reach the minimum, which is ideally 0. That's why we have what we call the saturated gain coefficient. So the theory or the concept beyond this solution is that the gain coefficient that you are using each round trip to multiply your signal with is a decaying gain coefficient. Herein, we have this gamma of mu, but we assume that this gamma of mu is fixed. So each time the signal, the transmission resonance is multiplied and amplified. However, realistically, the equation will be looks like that, which means that per each cycle, your gaining coefficient is attenuated with respect to the intensity. The higher the intensity, the lower the gain coefficient. You can plot it. I recommend that you to plot it. Just you can make it over MATLAB or over any Excel maybe or any tool. Just plot in the x-axis. Let me make it now here. Okay, that's perfect. So just use a pen. So this is, for example, the x-axis, which is the intensity, and this is the y-axis, which is the gamma. So you will find that gamma is maximum when the intensity is equal to 0. So I just need to change the pen. Okay, let's use, for example, yeah. So at 0, it's equal to gamma node, and then it will going to decay like that. So whenever the gain tends to, whenever the intensity tends to 0, sorry, it tends to infinity, that gain coefficient or gamma will tends to 0. So this is a very interesting solution to show that the amplification gain or the gain associated to the optical cavity is a saturated gain and not it's an infinite gain. Okay, maybe you can ask yourself, okay, you reach this equation based on some givens. You assume that N2 is much greater than N1. You assume that tau2 is much greater than tau1. You assume steady state. So this solution is a restricted solution under a given assumption. It's not a general solution, which is 100% true. So let's now resolve it again, but without neglecting N2. Sorry, without neglecting N1. So I will cancel this assumption. Let's assume that N2 and N1 are comparable. N2 is not much greater. It's only greater than N1, not much greater than N1. This the mathematical derivation is found in the lecture script. However, you are not requested to do it. I'm just showing it to you for understanding. You are not requested to make it step by step. However, for the first one, you are requested to do it, of course. So here will be the solution. Of course, it's more and more complicated because now your differential equation will be a function in N1 and N2. So you have to solve these two differential equations together to get N1 and two equations together to get N1 and N2. By the way, in case number 2, we're still assuming a steady state. So you can kick out this dn by dt and put 0. So you will have two equations by two unknowns, and you're going to solve them together to get N1 and N2. So this will be N1 and N2, very large. However, if you start to do the same procedure and calculate gamma, you will find that gamma will have the same look. Gamma equal gamma node, but now gamma node is a very large term. 1 plus I over IS, typically the same. Let me use my pen to clarify. So all this term is gamma node, and all this term is IS. So simply, it's typically the same equation. The only difference is the definition for gamma node and IS become more complicated. but still the saturation condition occurs for gamma. For higher intensity, lower gain coefficient. That means that this concept is sustained regardless the assumptions. This is very important to understand or to validate the concepts. Okay, perfect. Now we are still assuming that that we are working in a steady state condition. Now let's even don't assume a steady state condition. No steady state. So we are not going to solve a linear equation. We are going to solve a differential equation. Again, this is not required from your side. You are not requested to do it step by step. So there is no approximation that works. In this case, we will have N2 in this manner and N1 in this one manner. Of course, now N2 is a function in time because it's now a time dependent because no steady state. That's why we have this equation as a function in time. And under this condition, we will get these two curves. This while assuming that tau2 is greater than tau1, and this while assuming that tau2 is smaller than tau. Why we are intended to plot these two? This is very important. Please now observe with me these two curves, N2 and N1, and here N2 and N1. Do you recognize something? Just please, just please recognize this area. In this area, N1 is greater than N2. As you can see, in this area, N1 is greater than N2. So where is the problem to have an N1 greater than N2? If you have a good memory, you will answer it quickly. This is simply a problem because the condition condition for a gain or the gain condition is to have N2 all the time greater than N1. So that means that whenever N1 is greater than N2, you will not have a gain, you will not have a laser. That's why we have two options here. What we call a continuous wave laser and what we call a pulsed laser. Why this is a pulsed and why this is a continuous? This is continuous because all the time tau2 is greater than tau1, N2 will be greater than N1, so laser will be conducted all the time. However, herein, per each injection cycle, there will be a period where the gain condition is not fulfilled. So your laser will only operate in this region. But in this region, no laser will operate. That's why the output will be a pulsed laser, not a continuous laser. Okay. Now we have answered together the first question, which is, do we have an infinite gain loop? No, we don't have an infinite gain. We have a finite gain. We have a saturated gain. The answer was here. But if you remember, by the end of the previous part, I have asked you another important question. Why we are using 3 levels to construct a laser? When we start Einstein approach together, we have started with only 2 levels. Why we need 3 levels to conduct a laser? This is a very important conceptual question. The answer, my dear students, the answer is here. Let's describe it together. This is very interesting. Okay. Let's start with an Einstein approach. Or let's make it in a comparison manner. So Einstein approach was discussed on a 2 level, E2, E1, and E2. However, what we have implemented together is a 3 level. Okay. We agreed together that in order to have a gain, we should have N2 greater than N1. Okay, perfect. So let's assume that we have N2 greater than N1. So the starting will be that you have a lot of particles here. And a few particles in N1. So now both systems fulfill the condition. N2 is greater than N1. In order to have a laser, you will assume that a group of these photons will stimulate to energy level number 1 and emit a group of stimulated photons in addition to the instant photons. Typically the same here. So now you have a laser, you have an incident. This incident is amplified due to the stimulated emission photons coming from E2 and going to E1. Similarly here. Perfect. So the question is, once this process is done, that's logically mean that the popularity of N1 will be greater than N2, because simply a huge amount of the photons in E2 of the or a huge amount of the electrons in E2 goes to E1 to produce stimulated emission photons. Then the laser condition will not occur. So it's an instantaneous laser. It's an instantaneous laser. That's true? Yes. But how we are going to solve it here? We are going to solve it here in a very easy manner. To use a storage level, which is easy. It's as following. Electrons will jump from E2 to E1 perfectly. However, we will adjust E1 to have a very, very small lifetime. Remember, tau2 greater than tau1. So once these electrons reach E1, it will instantaneously go back to E0. Then, don't forget, you have an injection rate, which is R2, which will inject electron back to this energy level, to the energy level E2. Accordingly, in the 3-level laser, you can sustain the condition that N2 is much greater than, or is greater than N1. However, you will not be able to do it here because you don't have this storage ground. Electrons will go back to E1, then automatically E1 or N1 is greater than N2, so you don't have a laser. And you need to inject back these electrons here, so you will return to the condition, and then you don't have laser and so on. But here, you will have this continuous effect where N2 is greater than N1. That's why it's impossible to create your laser using a 2-level model. You should use at least a 3-level model. Okay. By the way, please think again about R2. From where you get these R2? This is a very important question. Okay, let's now return back to the presentation slides. And now we understand why we need a 3 levels in order to implement a laser. And let's now go to, this is for you. It's not only 3 level. We also have a 4-level laser. Think about it. Maybe you can see it in your exam. Maybe you can solve it and discuss it with me if you like so. What is the advantages of having a 4-level laser instead of a 3? It's still the stimulated emission or the laser area is this area. This one, let me show it again. This area is a laser area. But now you have an upper storage and a lower storage level. So instead of having a lower storage level, you have a lower storage level and an upper storage level. But what is its benefits? Think about it. This is for you to study it and to understand it. And please feel free to comment or to discuss with me your thoughts about why we should have a full level laser. That's perfect. Okay. So let's go to the next. Okay. Now let's go to, let me open the laser again. Okay. Now let's go to a very final short division in order to understand the concept of the gain and how this concept is important. So we will start with this equation. Gamma equals I over I node di by dz. Actually, this is a very common equation. We use it more than one time. So I will return back to my whiteboard and we'll start. Here. So let's start with the general equation. Di by dz equals gamma times I. That means that 1 over I di by dz is equals to gamma. We have concluded that gamma equals gamma node 1 plus I over IS. So you can easily remove gamma from this equation and substitute with its equivalent. So 1 over gamma, 1 over I, sorry, di by d as z equals to gamma node times 1 plus I over IS. It's a differential equation. You can shift this term to the left-hand side just to make all the I term in one side and all the gamma terms in one side. So let's do it. So it will be 1 over I. Let me use another one. 1 over I times 1 plus I over IS di equal gamma node dz. So 1 over I, let's multiply by the bracket. So 1 over I plus 1 over IS di equals to gamma node dz. Now you can integrate both sides. You will integrate the di with respect to the input to the output. So now this is integration of 1 over I plus 1 over IS di from I1 to I2. So I1 is the instant and I2 is the output, equals to integration of gamma node, which is a constant, dz, over the distance or the length of the material, which, if you remember, Lg, so from 0 to Lg. 1 over I, the integration will give you len, so it will be len I2 over I1, plus, here Is is a constant, so 1 over Is times I2 minus I1. And then you have, this is of course a constant, so gamma node times Lg. So L2 minus over L1, this is the output intensity over the input intensity. So this is the gain. So len, the gain, plus, if you pick up I1, which is the incident outside, so it will be I1 over Is times the gain minus 1, because now I2 over I1, which is the gain, equals to gamma node Lg. And this equation that demonstrates or that links the gain coefficient, the gain of the gain coefficient, I2 over I1, the input in intensity, I1, the saturation intensity, Is, and the length of the material, Lg, and the initial gain coefficient, gamma node. So you can use this equation directly to link these parameters together. This is just a linking equation to link parameters together. So let me return back to the presentation slides. here, and now this is the final equation you have, that gamma node LG equals length the gain plus gain minus 1 times I1 over IS, where I1 is the incident intensity. This is the termination of chapter number 5, which is the the laser oscillation and amplification. One more chapter is waiting for us, which is light propagation in the form of Gaussian beams, or laser propagation in the form of Gaussian beams. This will be our terminating chapter number 6. So see you in next week, in next chapter, and hope that you enjoyed the lecture, and good luck with your next chapter, inshallah. Thank you very much, and bye-bye.